1.5, inverses of functions. There are definitions here that you do need to know. Inverse is a function that undoes the action of another function. Simply put, applying f and g is the same thing as doing nothing. The most common occurrence of you knowing about inverses to this point in your math career is about inverse operations. So multiplication is the inverse of division, and division is the inverse of multiplication. It goes both ways. They undo one another. Same with addition and subtraction, squares and square roots, etc. There are 3 different definitions. The first is an algebraic definition, and it says that if you take f of x and plug it into g of x, it should simplify to x. And vice versa, if you take g of x and plug it into f of x, you should get x out. The graphical definition is that it's symmetric across the line y equals x. And another way of thinking about it is that the first and second elements of each pair in the original function are interchanged. In other words, we swap x and y. The way that we write inverses, the inverse is denoted by f to the negative 1 of x, and we say inverse of f. It is important to note that this is not the same as 1 over f of x. I know that previously you would have learned that negative exponents meant that you should move them to the denominator. The placement of this negative 1 is what differentiates it. So this says inverse. This would say that it's an exponent that needs to move down. Some functions are what we consider one-to-one, and meaning that every input has its own unique output. Remember that in order to be a function, something must pass the vertical line test. In order to be a one-to-one function, something must pass what we call the horizontal line test. So let's start with that, actually, and decide whether or not the graph is a one-to-one function. So first of all, is it a function? Yes. Is it one-to-one? No. In multiple places, it hits the function more than once. So, no. For B, yes, it's definitely a function. Yes, it is one-to-one. And for C, it's definitely a function. It very much fails the horizontal line test, so this one is not one-to-one. The reason that this matters is that in order for a function to have an inverse, it must be one-to-one. So inverses don't exist when a function is not one-to-one. So let's just remember how to deal with these tables. If we were to find the inverse, all we have to do is switch our x's and our y's. Once x and y are switched, all we have to do then is answer some questions here. F of 6 would say, okay, if x is 6, what is f of 6? F of 6 then is negative 4. And the reverse is also true, that x would therefore need to be 6. Now it asks us to find the inverse of 4. So now we're going to look at this other table. Inverse of 4 is negative 2. Going the other direction, if the inverse is 8, what is x? Negative 10. When it comes to a graphical definition, there's kind of 2 ways to think about this. You can think about the reflection across the line y equals x. However, because it's a diagonal, sometimes it's a little bit easier to do it in table format. So I would create a table of your ordered pairs. So we have a point at negative 3, 4, a point at negative 2, 1, point at negative 1, 0, and a point at 4, negative 2. So if we were to create the inverse, we would get points at 4, negative 3, 1, negative 2, 0, negative 1, and negative 2, 4. Then all that's left is to graph those points. It is important to note that this one inverted is here, this one inverted is here, this one inverted is here, and this one inverted is here. And please note that the open circles do stay as open circles. And you can very clearly see that visual representation that they are in fact inverses. I always like to have that y equals x line on there when I'm dealing with inverses. Even if I don't use it to do the actual reflection, I do appreciate being able to double check the work visually. All right, so if we have a point at -2, 0, then we need to have a point at 0, -2. That is going to reflect right across to there. This point was at -1, 1. So we need a point at 1, -1. And I like this point here also. This is very nice because it's actually already on the line that we're supposed to be reflecting across. So this one looks like that when it is inverted. One way you can think about this is as if this is a line perpendicular, then it's going to go to the exact same spot on that perpendicular line. Perpendicular 1, perpendicular 1, which is why this one just stays right there, if that helps you visualize what you need to do. The next definition we're going to deal with is the algebraic definition that says that f of g of x should equal x, and that g of f of x should also equal x. So this is how we do this. We check these and see what they come out to be. So let's start with f of g of x. F of x has our cubed root here. Our x then, though, is going to be x cubed plus 1, and then we're going to subtract 1 there. Of course, we don't really need these parentheses if we're just subtracting, so those two will cancel out, and we get the cubed root of x cubed. Well, of course, the cubed root of x cubed is just x. And we're going to check the other way too. We're also going to check g of f of x. So this time we're going to have the cubed root of x minus 1 to the third power plus 1. Those will cancel, giving us x minus 1 plus 1. Those will also cancel, leaving us with just x. So indeed, f and g are inverse functions of one another, and that makes sense. How do we undo cubes? With cube roots. How do we undo addition? Subtraction. This was on the outside of that function, so it's got to come to the inside. Let's do another. F of g of x would place this x minus 5 over -3 into the x spot here, and we would have 5. Of course, both multiplying and dividing by -3 make 1. Then we are left with x minus 5 plus 5, which leaves us with just x. Going the other direction, we would have -3x plus 5 minus 5 divided by a -3. Those make 0. Those make 1. And we are left simply with x. So in this case, f and g are also inverse. Notice that we subtract 5 to undo that one. We divide by -3 because this one was multiplying by -3. So we have to do those inverse operations in the order we would do them. If we were to solve for x here, we would first subtract by 5, then we would divide by -3. That is the inverse. Next, we are going to talk about the one-to-one requirement and how we would actually go about finding an inverse function. So for this one, if we want to find an inverse, first I would always check your domain. So the domain tells us that we can't take the negative even root. So this has got to be greater than or equal to 0. So x therefore has to be greater than or equal to 2. I would just hold on to that because it's going to ask us right here. Now that we have that domain, let's go ahead and find the inverse. So the steps to do this are going to be 1, to switch x and y. So we're going to have x equals 5 minus the square root of y minus 2. Next, we need to solve for y. So order of operations tells us we got to do the stuff that's furthest away first. Subtracting 5 cancels there, so we've got x minus 5 equals the negative of the square root of y minus 2. We can get rid of that negative by dividing by -1. So that leaves us with -x plus 5 equals the square root of y minus 2. Now we can square to get rid of our square root, and then we can just add 2. We get y equals -x plus 5, quantity squared, plus 2. The last step here would be to switch our notation. We're going to go ahead and put our inverse notation. So our inverse is the quantity of -x plus 5 squared plus 2. Now, range is actually pretty tricky to find here unless we graph it, which we could. We certainly could just go ahead and graph this. So let's try that out. Okay, so this is our parabola after we have shifted it left 5 and up 2. But remember, this is the inverse. This isn't what we started with. So let's go ahead and graph what we started with also. So what we started with was a square root that had been reflected across the x-axis, moved right 2, and down 5. So that's going to look like this guy. The reason that this looks so strange here, if we're saying this is this, and then this is our reflection, and that doesn't look like that reflection, what gives, right? What's going on here? Well, in order for this inverse to exist, we need to restrict its domain. We can't just plug whatever we want to in here, because we need to keep it 1 to 1, and this is not right now. So this is kind of a fun thing though. The domain of f becomes the range of the inverse. The reason for this is that the definition of an inverse is that x and y are swapped. Well, domain is all of your possible x values, and range is all of your possible y values. So if we switch x and y, our domain and range are going to flip around like that. So let's think now, what would the range of this guy be? Well, the highest it would ever go would be to -5. So this one is saying that y has to be less than or equal to -5. Which in turn would then make our domain being x is less than or equal to -5. Well, that would be only these values. If it's less than -5, it's got to go this way. So what happens here is that we pretend none of this exists in order for this to be a 1 to 1 function so that it can have its inverse. Let's do another one to make sure we understand here. This one is really interesting because we start the other way around. It's very similar. So let's go ahead and get our graph. Now, if we were to do this parabola, it's shifted down 25, and to the right 5. So now that this is here, it very clearly states that x must be greater than or equal to 5. So what it's saying is, hey, I'm only looking at this piece. This one doesn't exist, because it told me that this is only true when x is greater than or equal to 5. This works similarly to how piecewise functions worked. This is saying that, hey, this is only true of f of x when this is happening. Everywhere else, it's not what's going on. But when x is greater than or equal to 5, this is the function. Okay? So the first thing is that the domain is actually already given to us. It has already told us that our domain is 5 to infinity. The range, therefore, has to be that same way. Okay? So let's go ahead and find our inverse. So we switch x and y, and then we need to solve for y. So we add 25 to both sides, which results in x plus 25 equaling y minus 5 quantity squared. Then we need to square root to get rid of our square, which results in the square root of x plus 25 equaling y minus 5. Then we add 5 to both sides, and we get the result. The square root of x plus 25 plus 5 equals y. Then we switch to our proper notation. And we get that the inverse of f equals the square root of x plus 25 plus 5. I would like you guys to notice that minus 25 started on the outside, and we end up with plus 25 on the inside. The inverse of squaring is the square root, and minus 5 started on the inside, and we result in a plus 5 on the outside. That is not coincidence. That's because they're inverses. Okay, so then we would have to check our domain and range here. The domain of the inverse here tells us that the square root of x plus 25 is the only restriction, and x plus 25 therefore has to be greater than or equal to 0. Therefore x has to be greater than or equal to negative 25. So our range for this one is from negative 25 to infinity, which means that our range on this one was negative 25 to infinity. And I want you guys to take a look here. Isn't that what the range was? And it was the domain here. So those do truly switch when that happens. If you would like the visual to see what the inverse would look like, it looks something like that, because the square root function would be shifted left 25 and up 5, which is indeed that reflection. So again, the big takeaway here is that the domain and range switch places because x and y switch places. It is significantly easier to find the domain of the inverse and then know the range of the first than it usually is to find the range of the first. So just keep that in mind. These ones wouldn't have been too bad to find a range. You could have done it graphically, but often the range is very difficult to find. So it's easier to find the inverse and find the domain of that inverse. A few more examples of these where it is a little bit more complex. Again, I would probably start by finding the domain. So 3x plus 4 cannot be 0 because we can't divide by 0. Then I would go ahead and find the inverse by swapping x and y. Now this is interesting because you have to do it everywhere that you see an x. Everywhere that it was an x becomes a y. Now this is doubly interesting because now we have two y's. Which one are we solving for? So there is a very specific trick to these types of problems. So you're always going to want to start by multiplying by the denominator, which cancels here. But on the left side, you're going to want to go ahead and multiply that in. So 3y times by x gives you 3xy, and 4 times x gets you a 4x. And on the other side, we just have 2y minus 1. Now you're going to want to get everything with a y to the left side, everything without a y to the right. So we're going to subtract the 2y over here. We're also going to subtract that 4x. So the 4x will cancel on this side, the 2y will cancel on this side. And what we end up with is 3xy minus 2y equals negative 4x minus 1. Now here's the big trick. Factor out your GCF of y. That leaves you with 3x minus 2, and it equals negative 4x minus 1. Now you have only one y, and all you have to do is divide away the part that's being multiplied. Then we get that y equals negative 4x minus 1 divided by 3x minus 2. And in our proper notation, f inverse of x equals negative 4x minus 1 divided by 3x minus 2. Now, there is a very distinct pattern to what happens to these numbers. You'll notice that this 2 started here, ended up down here. This 1 started here, stayed there. This 3 started here, stayed 3. But what happens is that those two become negative and switch places. Okay, that does happen every single time. It's kind of an interesting that happens with rational functions. So our domain of our original was that x could not be negative 4/3. If we were to write that in interval notation, it would look like this, which is often how I'll ask you to write it. All we have to do is exclude that negative 4/3, which means that the range is that y can't be negative 4/3 for the inverse. And I did want to point this out. You could have found that right there on the inverse. But the interval notation would be identical. Now the range, again, finding the range of this one is a little bit tricky. You have to remember all the different rules to doing that. So it's actually easier to go ahead and find the domain of this one. And we get that x can't be 2/3. In interval notation, that would look like this. And therefore the range of f is that y can't be 2/3. The interval notation is identical. I told you it is a little bit trickier to find the range, but if you do remember how the coefficients would be divided here, because the exponents are the same, if that sounds familiar to you, that might be helpful to you to check your work. But it does come out as that 2/3. Here's another example for you. Again, I usually find domain first. So we get that x cannot be 1/3. I'm going to go ahead and write it in as the range right now, because I already know that. And I'll go ahead and find my inverse. We do that by replacing every x with a y, and then trying to solve for y. We actually solved this in the exact same manner as the last one. We multiply by the denominator, Go ahead and multiply that in. Then we get everything with a y on one side, everything without a y on the other. And we get that negative 3xy minus y equals negative x. Factor out our y and get that y multiplied by negative 3x minus 1 equals negative x. And then just divide by our negative 3x minus 1, which results in y equaling negative x divided by negative 3x minus 1. Now, because all three of these do have a negative, you can actually get rid of it. You can think about it this way. Negative 1 times by x divided by negative 1 times by 3x plus 1. Our negative 1's cancel, and we can say x over 3x plus 1 if that's helpful to you. Now, of course, though, we do need our proper notation. So our inverse here is the x over 3x plus 1. So our domain of our inverse is that x cannot be negative 1/3. So therefore the range of our original would be that y cannot equal negative 1/3. Here's one more type of problem that you might see, and I think it's very helpful to have a graph here. So x plus 4 squared, remember, would move our parabola to the left 4. So the problem is that we need a domain that is 1 to 1, and this parabola is not 1 to 1 right now. So it's saying find a domain on which it is, but also it needs to be non-decreasing. Now remember, non-decreasing just means increasing. So it's specifically asking us for the part that's increasing. This is the part that is increasing. So what it's saying is we only want to deal with that domain. Well, the domain of that would be from negative 4 to infinity. And we're going to pretend none of this exists. Okay? And we could actually do the range from here right now if you wanted to, because we had to graph it anyway. So I would say the range then is from 0 to infinity. Now that we have it restricted to a 1-to-1 domain, where we're only dealing with a function that is 1 to 1, we can go ahead and find an inverse. So again, let's just switch our x and y's. So x equals y plus 4 quantity squared, and then find the inverse. So let's go ahead and take the square root, which cancels our squared. We get that the square root of x equals y plus 4, and we actually don't need our parentheses anymore. And then we can subtract by 4 on both sides, which results in y equaling the square root of x minus 4. And with proper notation, f inverse of x equals the square root of x minus 4. Now, if we were to find the domain of this, you can very clearly see, like, well, that just can't be negative. So it's just that x is going to have to be from 0 to infinity. Of course, though, we did move it down 4, so our range is going to be negative 4 to infinity. And if you look, those are indeed just switched.